what we can get to today. So, we had finished up on Monday talking about inorganic components of living things. So we talked a lot about water, that's a really, really important inorganic compound, and we talked about salts that can be electrolytes. So we finished up inorganic things, and today we're going to start organic things. Okay, so these are things that contain carbon. But remember, inorganic things are just as important as organic. I don't know what I'm trying to say, they're both important. Okay, so carbohydrates will be our first organic compound we talk about today. But before we talk about specific types, let's talk about two different terms. I don't think it clearly states it in our notes, but we're going to start a little chart over here to kind of make things easy. Okay? So what is the difference between a polymer and a monomer? Can you tell me? Yeah, so a monomer is a small building block, and if you put enough monomers together, you end up with a polymer. So, for instance, I've got monomers, which are little paper clips. If I stick them all together, I end up with a polymer of paper clips. Okay? And the terms polymer and monomer are very, very, very general. So we're going to talk about polymers for the organic compounds. The carbohydrates are polymers, nucleic acids are polymers, proteins are polymers. But you also see polymers used out in general workplace in the world. So the non-stick coatings on frying pans, those are polymers. PVC that makes up the pipes in buildings, that's a polymer. Okay, so anything where you have smaller subunits that you stick together to make something bigger is a polymer. Okay, so what we're going to talk about today are a couple different types of polymers. Okay, so I'm going to make this a little chart. And we're going to add to this as we go throughout class today. We weren't going to finish it, but there'll be some left to do on Friday. Okay? But our first class that we're going to talk about today are carbohydrates. Carbohydrates are organic, so they have carbon. They're also a polymer. Okay, we'll get to our chart in a second. So can you guys tell me, what are some things that you like to eat that are carbohydrates? Pasta, yes. What else? Bread, cinnamon rolls, yes, love cinnamon rolls. IKEA, do you guys go to IKEA frequently? Okay, so we just moved to Fishers, and we are right next door to the IKEA, and so frequent Sunday afternoon trips to let Deborah jump on the beds, and to get a bun. That's what she likes to do, is get a bun. So we eat our bun at the IKEA with our free coffees. Okay, so cinnamon buns are carbohydrates. What else? Donuts. That kind of fits in the cinnamon bun category, doesn't it? Okay, so all the things that you've mentioned so far are the polysaccharides. They're the big sugars that are made up of lots of little sugars stuck together. Does anybody know a simple sugar? A little one. Huh? Glucose. So glucose is a simple sugar. What do you eat that may have glucose in it? Fruits have glucose in it. They also have fructose in it. Fruit sugar. Oh, look how excited you are, Dog. It's great. Okay, so fructose is fruit sugar. Okay, candy has table sugar in it. Okay, so table sugar is made of glucose and fructose stuck together. Okay, so there's lots of different types of carbohydrates. Okay, so what defines a carbohydrate? First of all, they contain carbon, hydrogen, and oxygen, and that's it. So these guys I like to call the toes. Carbon, hydrogen, and oxygen. And specifically, the hydrogen and oxygen atoms are going to occur in a 2-to-1 ratio. So for every one oxygen you have, you're going to have 2 hydrogens, which we'll get to on the next slide. Okay. They are classified according to their size and solubility as either a monosaccharide, a disaccharide, or a polysaccharides. And the monosaccharides are the structural building block of all of our carbohydrates. So, now that we know that, let's see if we can break that apart and put it in our chart. That kind of rhymes. That's good. Okay, so our carbs. First, let's see if we can figure out what are the monomers. What are the individual building blocks? From what we talked about on the slide, what are the monomers of carbohydrates? Monosaccharides. Okay? So those are going to be the smallest the smallest sugars. And when you see them on a picture, which will be on the next slide, they're just going to be one ring. That's it. If we put two of those monosaccharides together, what do we end up with? A disaccharide. And if we put many monosaccharides together, we end up with a polysaccharide. So what's our polymer? A polysaccharide. So, polymer and monomer are very, very general terms. When we use those terms specifically for carbohydrates, the monomer is now called a monosaccharide, and the polymer is now called a polysaccharide. Okay? We're just replacing monomer and polymer with specific carbohydrate terms. Okay? Now, questions with that? Okay. Now, even the terms, let me draw a picture of our polysaccharide. Okay. So we've got a nice little chain of our monosaccharides stuck together. Now, on this next slide, let me read the bullet and then we'll look at the picture and talk about a couple other things. So first of all, you need to know this general formula for a monosaccharide. Okay? It's going to be CH2O N, where N is going to be the number of carbons in the sugar. So for example, if we're looking at a 6-carbon sugar, like glucose, we're going to have C6, because there's 6 carbons, H. How many hydrogens are there going to be? Using our general formula. 12, because for every 1 carbon, there are 2 hydrogens. So there are going to be 12 hydrogens in this case. And how many oxygens will there be? 6. So C6H12O6 is the formula for glucose. Okay? What if I had a 5-carbon sugar? It would be C5, H10, O. So if you see a chemical formula with that ratio, CH2O, you should look at it and say, that's a carbohydrate. Okay? This was one of your objectives, be able to recognize the structure of each of the classes, which was what was quizzed on that first slide in the quiz. So what do you guys look for carbohydrates? How do y'all remember it? Yeah. Well, how do you remember the structure? What these guys look like? They all have what? Oh, okay, sometimes. Okay. So we call them rings because that's the chemical name for them. They have a ring or a circle, but they look like stop signs. Okay. Now these, some of them you'll see have 6 sides. Some of them have 5 sides. We could call them something a little bit different. So if it has 6 sides, it's a hexose. If it has 5 sides, it's a pentose. Based on how many carbons are in a ring. Okay, that's not important. And also notice on this slide that there's not just one monomer for carbohydrates. There's lots of different types of monomers. So for example, a glucose is a monosaccharide. It is a type of monosaccharide. Okay? So a type of monosaccharide is glucose. Okay? Another monosaccharide is fructose. And there's the lactose, there's ribose, there's lots of other different types of monosaccharides. Okay? But because they're only one ring, they are still considered monosaccharides. Okay? Then, to make a disaccharide, we take any two monosaccharides and stick them together. So, sucrose is table sugar. So what you find in little packets. Okay? And it is specifically a glucose and a fructose stuck together. So if you stick glucose and fructose together, you are always going to get sucrose. Okay? If you stick two glucoses together, you get maltose. If you stick a galactose and a glucose together, you get lactose. So we can take all the different types of monosaccharides and combine them in all types of different ways to end up with lots of different sugars. Okay? So the monosaccharides are just the building blocks, the little Legos that you stick together. Okay? Then, polysaccharides, we're just talking about big long chains. Okay? So our example here is glycogen, which is found in you. You have stores of glycogen in your cells. And glycogen is made by a whole lot of glucoses stuck together. It's just a long chain of glucose, 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 glucose. So you store your glucose away, but then when you need some glucose, you just go back to that glycogen and you break off one. You say, hey, there's a glucose, I can use it now. And then you go break off another one and you can use that glucose. Okay? So we store away glycogen, but then we can get it out through the ether. Okay? Now, the formation of a polysaccharide. Well, this example is a disaccharide. We're only sticking two things together. Okay? But if we've got a glucose and a fructose, and we want to stick them together to make a sucrose, what type of reaction are we going to do? Dehydration. Okay, so going this way is your dehydration synthesis. Okay? To synthesize means to build, to put together. So in order to synthesize a polymer, you have to use a dehydration reaction. Okay? Then, if we want to go the opposite way, so now we ate sucrose, but we want to break it down in our body. We want to get the glucose and fructose out of it. How are we going to break this bond? What type of reaction? Hydrolysis. And that's going to send us back this way, and we're going to end up with two monosaccharides. We're going to end up with a glucose and a fructose. Okay? All right. Okay, I think the next slide is lipids. Are there any questions about carbohydrates? Oh, no. We are not ready for lipids yet. We're going to talk about the functions of carbohydrates first. Okay, so why do we eat carbohydrates? Energy, right. And the energy that we get from carbohydrates is ready and easily used. So it's going to be quick energy. We may put some in glycogen for a little while, but it's not going to stay there very long. Okay, specifically, our body likes glucose. And glucose is going to be broken down by most cells to produce ATP. And if we don't know about ATP yet, we will get to it at the end of this chapter, and we'll spend some time with it. And we'll see how it does its job. But ATP is the form of energy that our body needs. We get it from glucose. Okay, so that's the energy end of things. Carbohydrates are used for energy. But carbohydrates can also be used for structure. So in our body, DNA and RNA have that sugar phosphate backbone on either side of the DNA rung, or either side of the ladder. Okay, so that gives structure to DNA. So no carbohydrates, no DNA, no DNA. Okay. Carbohydrates are also found on the surface of cells. Okay, to help other things know what that cell is. Another example of structure that isn't on the slide, it is not human anatomy, so it's not important for this class, but I'm going to tell you anyway. So when you step on a bug and it goes crunch, that crunch is the chitinous exoskeleton on the outside of the bug. And chitin is a polysaccharide. So it's the pressure, sugar. All right. Tell that to your friends next time you see the bug. Practice exoskeleton. You'll impress them. Okay. And finally, if your protein intake is too low and you don't have enough protein to help build back your muscles, then some sugars can be converted into protein, which is pretty cool. It's kind of magical how we can shift from a carbohydrate into a protein. But we'll talk about that later. Okay, now I think we are finished with carbohydrates and ready to go on to lipids. Yes. Okay. So, while I put this up on the screen, can you guys tell me what are some examples of lipids? Phospholipids. Yep, we're going to get to those in a second. What else? I heard lots of different answers. I don't know what y'all said. Mostly you said fats and oils and triglycerides and cholesterol. Y'all had all those things. Y'all said all of those all at the same time, right? Yeah. Perfect. Okay. So all those things are lipids. Okay, so they all fit under the umbrella term of a lipid. Okay, those are all different examples. They are also CHO. So they also have carbon, hydrogen, and oxygen. But they are not in that CH2O formula. Okay? They're in different proportions. There's lower oxygen than what you see in carbohydrates, but there isn't a general formula for them. Okay, so we don't have anything for you to memorize to look at and say, that is a lipid. Okay? Just remember that they're carbon, hydrogen, and oxygen. Some of the more complex lipids will also have phosphorus. And we have neutral fats, which are your triglycerides, we'll get to in a second, phospholipids, steroids, and other lipoid substances. Oh, and I forgot this first bullet. It came up while I was talking. But it relates to the funny picture that's on the screen. So, lipids are insoluble in water. So water, we said, Wednesday, is a really, really good solvent. Lots of things like dissolving. Why? What makes water a good solvent? It's polar. It's got both a positive and a negative side. Fats, lipids, are non-polar, so they don't like water. The fats do not dissolve in water, which is why the polar bear is dissolving, but the non-polar bear is not. That's funny. Some of y'all are just scared. Okay. Okay, so different types of fats. So these are things that fit under the umbrella of a lipid. Okay? Now, one thing to note before we get too far into here is that lipids are not polymers. Okay? This is our type of organic compound that is not a polymer. So he doesn't have a monomer per se, and we're not going to add him to our chart. Okay? So this first type of lipid is called a neutral fat. From this picture, what's another name for neutral fat? Triglycerides. And that's what it is on your objective list. That's the way it was on the quiz. Okay, what do you see? What are there three of in the triglycerides? Fatty acid chains. Well, our answer is fast. I'm not going to drink my water. That's okay. This is not water drinking time. This is teaching time. Okay, so there are three fatty acid chains. Okay, so that's the tri in the triglyceride. And the three fatty acid chains are attached to is a carbon, hydrogen, oxygen chain called glycerol. Okay, so a triglyceride is three fatty acids attached to a glycerol. Okay, now, even though this isn't considered a polymer, the fatty acid tails are attached or stuck on using a dehydration synthesis. So we still build it by taking water out. And in order to break the fatty acid chains off, we use hydrolysis. Okay. All right. Okay, so triglycerides are named that because it has a 3-to-1 ratio of fatty acids to a glycerol. Okay, from what we just saw in the picture, 3 fatty acids attached to a glycerol molecule. Their job in the body is to store energy. So, let's say you ate all those carbohydrates and they gave you energy. with energy. Okay, so you have all those little monosaccharides floating around. But you don't do enough to use all that energy. So you're not very active. Okay? That energy that you ate in the form of carbohydrates then gets stored away long term as a fat. Specifically, these triglycerides. Okay? So these are the storage molecules. They store away energy for long periods of time. Okay, so that's considered our first function or characteristic of the fat. Okay? But things that we also get from this, it insulates our deeper tissues from heat loss. So it keeps you warm. That's good. It also protects you from mechanical trauma. It protects your organs when somebody tries to come up and beat you. It's also a good thing. Okay? Finally, the length and degree of saturation of the fatty acid chain determine how solid the fat is at a given temperature. Okay, what does that mean? I added a picture here to describe this. Okay, so our first chain here is considered saturated. A saturated fatty acid chain is straight. So saturated is straight. That allows those fatty acid chains to get really, really close to each other. Okay? And when it gets close to each other, it packs really, really tightly, and it's going to be more of a solid at room temperature. So, what is a lipid that you eat that is a solid at room temperature? Butter. Okay, so butter is an example of saturated fatty acid. What's another fat that you eat that's solid at room temperature? Okay, sour cream. Yes, sour cream has saturated fatty acid in it. Yes. What else? It's just I hadn't heard that example, but you're correct. Okay, what else? Yeah. Cream cheese will have saturated fatty acids in it. What about bacon? Okay, so what does bacon fat look like at room temperature? It's a solid chunk, right? So when you fry up some bacon and you save that bacon grease in the refrigerator in a jar, you guys do this, right? You save it in a jar, it becomes a white solid glob, right? That is a saturated fatty acid, or it's fats that are made up of saturated fatty acid. Okay, meats that have nice marbling in there, that marbling is saturated fat. Okay, so that's saturated. Saturated is straight chains, solid at room temperature. See how that all starts with the letter S? Isn't it great? Okay, the opposite of that is unsaturated. Unsaturated is not straight. In fact, in chemistry, we call it, already, instead of straight, it's kinky. So the fatty acid chains are kinky, which causes them to bend whenever it sees that double bond, okay? Which doesn't allow them to pack as tightly, which means they're not solid at room temperature, they're more liquid. So, unsaturated is kinky, and it is a liquid at room temperature. So what is an example of something that you eat that has unsaturated fatty acids in it? Oils. Yeah, so vegetable oils, olive oil, all those other oils, they are unsaturated. Okay, now, the third one on here, this is a specific type of unsaturated fatty acids. So trans fats. There are very few naturally occurring trans fats, but you can turn unsaturated fatty acids into trans fats by doing a process called hydrogenation, which means you just throw a bunch of hydrogens at it. Okay? And the hydrogens are going to get rid of some of the kinks, which makes it more solid. So, for instance, we can change vegetable oil into margarine by partially hydrogenating it, by adding more hydrogens, getting rid of the kinks, making it more solid. Now, the kinks that remain, though, are now, instead of looking like this, where they bend on themselves, that's called a cis double bond. The double bond is a little bit different. We call it a trans double bond now. And those trans double bonds do not do good things in your body. Okay? So there's kind of arguments about what exactly is happening in your body that makes trans fats bad. But they're either not digested themselves, or in the process of digesting trans fats, you can't digest good fats. So you're not getting those essential fatty acids that you need. Okay? Either way, they're not the best for you. Try to stay away from them. Okay? All right. So, those were triglycerides. Those are your storage fats. Now, next type of lipids are called phospholipids. Okay? These are fun lipids. So you see, he looks kind of like a triglyceride, except now instead of 3 tails, how many tails does he have? 2. He has 2 tails. He is missing his 3rd fatty acid. But it's okay. We took off that 3rd fatty acid, and in its place, we put this head, this phosphate head group. Okay, now, fatty acids are lipids, which means they are non-polar. They do not like the water. They are hydrophobic. Okay, but this phosphate head group that we put on is polar. So he likes water. He is hydrophilic. Now, okay, does anybody know the term for something that is both polar and non-polar at the same time? No, but that would be great. Okay, it's not bipolar. Answer. Amphipathic. Okay, so amphipathic means that it has both a polar and a non-polar part. It both likes water and doesn't like water at the same time, which is super cool. So we find these guys in the plasma membranes of our cells. Okay, so they're a chief component of cell membrane. Because here's what happens. You take 2 phospholipids, here are their tails. My elbows can be their polar head groups, right? And we flip one upside down. And now their fatty tails are in close to each other, and their polar heads are on opposite sides. This part doesn't like water. This part doesn't. So we can line the outside of the cell with that, and the inside can be water, and the outside can be watery, but they don't like to get near each other because there's this fatty lipid layer between the two. So it keeps what's inside, and keeps what outside is outside. It's cool. We'll talk more about it later. Okay, what you need to know now is that it makes up plasma membranes. We'll talk more about it. Okay, so we talked about triglycerides. We talked about phospholipids. Now, the third and last type of lipids that we ask you to know about are steroids. Okay, what did you guys think of to help you remember the structure of steroids? Anybody have something fun? No, it wasn't fun. When you were preparing for your quiz, what did you think of to help you remember that was steroid? Yeah. It does look like a BHAP. That's what I think of too. Okay, it looks like a BHAP. What else you got? Yes. Okay. Anything else? Any other ways to remember this is cholesterol? Okay. So structurally, what makes cholesterol are those 4 interlocking hydrocarbon rings. So we have rings like we see in carbohydrates, except now they're hydrocarbons. They're carbons and hydrogens, no oxygen there. And they're stuck together. Okay? So they're right beside each other. They share a side of the ring. Okay? The most predominant one that we see is cholesterol. And he is found in membranes, and he does lots and lots of good things. So we give cholesterol a bad rap. Sometimes he deserves it, but sometimes he doesn't. Okay? Without cholesterol, you'd be dead. Okay? So cholesterol is good. It's like the theme of this class. If this doesn't work, you're dead. Okay? And steroids are the building block for vitamin D. So vitamin D is that vitamin that you produce from the sun on your skin. Steroid hormones, so your sex hormones are estrogen and testosterone. And your corticosteroids are all made from cholesterol as a building block. And bile salts are also made based off of cholesterol. So bile salts are things that are produced in the liver, stored in the gallbladder, and help digest your food. Okay? All right. That is the end of lipids. Any lipid-based questions? Okay. Then let us move on to proteins. These are my favorite. I mean, I'm sure I sounded excited about carbohydrates and lipids, but I was just pretending. These are where it's at. Okay, so my graduate work, my research work, was all about making a brand new protein by going back to the DNA level and rearranging bases and putting them together and then making the DNA, put them into cells to make brand new proteins that help fight cancer. So they help turn on the immune system to come in and eat tumor cells. Okay, so I love proteins. Proteins do everything in the body. Okay, you ready for some examples? Okay, the first one on our list is structure. So structural proteins. An example is collagen. So it is the most prominent fiber in your connective tissue. It helps hold your body together. No collagen? You're dead. Okay. Enzymes. Enzymes help speed up chemical reactions. They help everything in your body run the way it should. If you don't have enzymes, you're dead. Okay. Transport proteins. So hemoglobin is a protein. It transports your oxygen all around your body. If you don't have hemoglobin, okay. Contractile proteins, actin and myosin, are found in your muscle. It's what actually moves your muscles around. If you don't have actin and myosin, you're dead because you can't move. Okay. Communication proteins are what deliver messages from outside of a cell inside of a cell. Guess what? If your cells can't communicate, you're dead. Okay, and finally, defensive proteins. So antibodies are defensive proteins. They go out and fight bacteria and viruses and other things that aren't supposed to be in your body and go kill it. And guess what? If you don't have antibodies, you're dead. So, proteins are really, really important. They're also a very, very diverse group. There's lots of different kinds of them. Okay? All right. Next bullet. They contain carbon, oxygen, hydrogen, and nitrogen. So now we are on to CHON. Carbon, hydrogen, oxygen, and nitrogen. They may also contain sulfur and phosphorus depending on what amino acids are present. Okay. And finally, last thing on this slide is that the amino acids are the building blocks of proteins. That means we need to go back to our original chart. Because proteins are polymers. Okay. What are the monomers of proteins? Amino acids. Does anybody know, did you read what's it called when you put a bunch of amino acids together? What kind of peptide? Polypeptide. Okay, I think I heard somebody say oligopeptide. Did somebody say oligopeptide? No? Did I just make that up? Okay, so a polypeptide is a long chain of amino acids, and oligopeptide is a shorter chain of amino acids. Guess what a dipeptide is? Two amino acids. Okay. And again, we have a bunch of different amino acids. So we have a bunch of different monomers. Okay? There's actually 23 amino acids in the body that are naturally occurring. So an example of this is tryptophan. Okay, where have you heard of tryptophan? You've heard of this? This is good. This is good. Where have you heard about tryptophan? Around Thanksgiving? Yeah? What has a lot of tryptophan in it? Turkey. Okay, and it's not accurate, but they say that the reason you get sleepy after Thanksgiving is because of all the tryptophan that's in turkey. But really, there's more tryptophan in chicken than there is in turkey. So you could use that excuse for like every time you eat poultry. So I mean that's there. Let's see, proline, serine. There's lots of different types of amino acids. Okay, and remember we said that there's lots of different types of proteins. It's a very, very diverse group. We have structural ones, we have enzymes, all that jazz. Each different protein has its own shape that allows it to do its job. So the shape of the glob determines the job. Okay? What we're going to be able to do with proteins is take these 20-some amino acids, put them in different orders in this long chain of amino acids to make a polypeptide. That will make the protein fold up into a specific shape, and that will give it its job. Okay? So the way we arrange these amino acids is very, very important. All right. Now, you guys know this already? Oh, I forgot to tell you about the structure of the amino acid. So it's on here on the slide. Every amino acid has a central carbon. It's going to have an amine group, and it's going to have an acid group. It's a carboxylic acid. Okay. So you have the amino acid. Get it? Okay. Then there's going to be another hydrogen, and then this fourth group is going to be represented usually in pictures by an R. We call it the R group. Okay. What makes tryptophan different from proline? There is something different in place of that R. Okay, so every amino acid has a different R group. It makes them different. Okay, so now we have two amino acids, and we want to form a dipeptide. How are we going to stick them together? Dehydration synthesis. We're going to take out the water. How are we going to break a dipeptide into amino acids? Okay. Now, we good so far with protein? Okay, I want you to take a deep breath. Now, what we're going to talk about next. It isn't super difficult, but it requires higher order thinking. Okay? It requires thinking in 3 dimensions. Okay, can y'all think in 3 dimensions? Okay. Barely. All right, so here we go. Remember, we said we have lots of different proteins, and they all have different jobs, and they all have different jobs because they have a different glob, a different shape of the glob. Now, we have to find a way to make that protein into its specific glob. Okay? So we are going to talk about the structural levels of proteins. Okay, so hang with me here. Okay, primary structure, the basic structure of a protein, we say is the linear sequence of amino acids composing the polypeptide chain. Okay, so that means we have an amino acid, it's bound to another amino acid, to another, to another, to another, to another, to another. If it's just a straight line just sitting there, he is in his primary structure. Now, the primary structure is really, really simple. Because it's just a bunch of amino acids stuck together, not folded into each specific shape. But it is super important because what amino acids are there and what order they're in is going to determine all of the other structures. Okay? Because what amino acids are there tell it how to fold. Okay. So primary structure is just the line of amino acids. Now, we're going to start folding it into the shape. So now, we're going to take that chain and we are going to twist it and bend it. Twist it and bend it into what's called the secondary structure. Now, with secondary structure, there are only two options. We can twist it into what's called an alpha helix, okay, which is a helix like the DNA strand, or it can fold into a beta pleated sheet, which is a little zigzag. Okay? So I'm going to draw, for our example up here, more of a beta pleated sheet. Okay? So now we have secondary structure of that polypeptide chain. It's folded a little bit. All right, now the amino acids that are there are going to determine whether it forms a helix or whether it forms a beta pleated. Okay. This is it. Okay. Now we're still not there yet because we just have twisties and we have bendies. Now, our next step is to form the tertiary structure. So, in the tertiary structure, the regions of the secondary structure are going to fold upon themselves to form a compact globular structure. Okay, here's what it's going to look like. You ready? This is accurate. Draw on the scale. Okay. Okay, so that is our tertiary structure. We've taken our secondary structure and we've folded it even more. Okay, but again, it all depends on what that primary structure told us to do. Okay. Now, some proteins, that's as far as it goes. We have one polypeptide chain that we folded and then we folded some more, and we're done. However, some proteins are even bigger and require a quaternary structure. When we get to quaternary structure, what we're doing is we're taking several polypeptide chains that are folded into a tertiary structure and sticking them together. Okay, here's what happens. We have one polypeptide chain glob, stuck to another polypeptide chain glob, stuck to another polypeptide chain glob, stuck to another polypeptide chain glob to end up with one big giant protein. Okay? Hemoglobin has a quaternary structure. There are 4 polypeptide chains to make up one hemoglobin protein. Okay? So, those are your layers of structures. Primary is just the amino acid chain. Once we start folding it, we get secondary. We fold that even more. We get tertiary. We stick a bunch of tertiaries together and get quaternary. Okay? This next slide is just the pictures that are not quite as good as the ones I drew on the board. Okay? So there's your amino acid chains, your helix or your beta pleated sheet. Then you get your polypeptide chain all folded together, and then you can put multiple polypeptide chains together. Okay? All right. How much time do I have? 2 minutes? Okay. So, the last thing I want to talk about, just so we're at the same spot as my other classes, are these proteins called molecular chaperones. So this is like inception in protein world. So molecular chaperones are proteins that help other proteins fold. Isn't that great? So they help the other proteins acquire their three-dimensional shape. So they prevent incorrect folding of the polypeptide chains. They also aid in the desired folding. So they keep it from doing what's wrong and help it do what's right. They help move proteins across cell membranes. And they help break down damaged or denatured proteins, which we'll get to on Friday. Okay? So it's just a group of proteins that do a little bit different job. Alrighty, so that is what we're going to talk about today. Friday, remember your homeostasis activity is due, as well as looking at chapter 3 objectives, so you'll be ready for class. But I think that is it. If you have any questions about anything, make sure you email me or come talk to me after class. Alrighty, see you guys later.